this lecture, you will be introduced to the concept of Fourier series and its significance in the analysis of networks and systems. You may recall that earlier we discussed the input-output relations of a linear continuous time invariant system with lumped parameters. Another way of describing a time invariant system is to say it is a system with constant parameters. And we also take the parameters to be real. So, if you have a linear continuous time system with lumped constant and real parameters, it can be symbolically represented as a box like this with an input and output terminals coming out. Now, we also observed that a characteristic signal for such systems is the exponential function. If indeed you have an input which is of the form f e to the power of s t, then the output will be h s f e to the power of s t. That means the input and output essentially have the same time functions, except that you have a proportionality function h of s. Any signal which gives rise to that property is said to be a characteristic signal or eigen signal. And in the case of the systems that we are considering, this exponential signal f e to the power of s t constitutes a characteristic signal. Now, in general, f and s can be complex. So, if s is complex, in general it will be s equals sigma plus j omega. Therefore, if you have a signal like that, when you substitute particular values of time, then the value of the signal turns out to be in general complex. So, it is only a mathematical tool that we use for the analysis of the system. In practice, a complex signal like that cannot be generated in the lab. However, the sinusoidal function of time, which plays such a vital role in AC circuit analysis, is a very close relative of an exponential signal e to the power of s t, as we will see presently. Therefore, we would like now to see how to relate this exponential signal e to the power of s t with the sinusoidal signal, and if the sinusoidal signal is the input, how we can obtain the output in terms of this h of s. So, let us see how it goes. We have seen just now that f e to the power of s t gives rise to the output. Suppose I have a e to the power of j theta replacing f, that is a constant, e j omega, that means I substitute j omega for s, then obviously the output that I get would be h of j omega, because s is now equal to j omega. In addition, you have a e to the power of j theta e to the power of j omega t. This is the characteristic function. Now, let me say that h of j omega being a complex quantity in general will have a magnitude h j omega and an angle alpha. Therefore, this can as well be written as h magnitude. I drop the functional notation j omega, a e to the power of j theta plus alpha e to the power of j omega t. Now, let me take another exponential function a e to the power of minus j theta e to the power of minus j omega t. Similar to this, except that the multiplying constant f is replaced by a e to the power of minus j theta, and instead of s equals plus j omega, I have taken s equals minus j omega. Naturally, this will give rise to h of minus j omega a e to the power of minus j theta e to the power of minus j omega t. So the difference between this one and this here now, instead of s equals you have minus j omega, instead of plus j omega you have minus j omega, and instead of theta I have taken minus theta. Now if the system parameters are real, h of s turns out to be, for a lumped parameter system, the ratio of two polynomials with real coefficients, and if that is so, then a property of such a rational function with real parameters in the real coefficients is h of minus j omega turns out to be the conjugate of h of j omega. H of minus j omega will turn out to be the conjugate of h of j omega, which means really that the magnitude will remain the same, but the angle will change. For a real parameter. What do we mean by real parameter system? Suppose you take circuit as an example, we are saying R, L and C have real values. Hence, I can write this as h magnitude a e to the power of minus j theta plus alpha e to the power of minus j omega t. Now let me imagine that we have a composite system which is the sum of these two. By virtue of linearity, the responses also can be summed up. So the sum of these two signals will give rise to a response which is equal to the sum of these two. Therefore, if you do that, then you have a e to the power of j omega t plus theta plus e power j minus omega t plus theta. After all, that is what we are having here. This will give rise to h j omega magnitude a e to the power of j omega t plus theta plus alpha plus e to the power of minus j omega t plus theta plus alpha. And indeed, you could now see that this is really 2a cos omega t plus theta. That means this is a general sinusoidal function of time, and as far the output is concerned, you have h j omega magnitude 2a cos omega t plus theta plus alpha. So what do we have? We have a sinusoidal function of time with an amplitude 2a. The output is modified, is also a sinusoidal function, but the output is modified in magnitude by this factor, magnitude of the h of s, which we call the system function, as you recall. Phase is also modified by an angle alpha. That alpha is the angle of h of j omega. Normally, when we deal with sinusoidal functions of time in AC circuit analysis, we use the phasors. Let us see how these are related to the phasors. In terms of phasors, we express this. For example, I think now that we have got this expression, I can drop this 2 here and this 2 here and simply deal with a cos omega t plus theta. Because after all, if this is reduced by factor 2, output also will be reduced by factor 2. The phasor for this, as you recall, will be written as a e to the power of j theta, a at an angle theta. and the phasor for the output is the magnitude h j omega a e to the power of j theta plus alpha. Now, h j omega times e to the power of j alpha, h j omega magnitude times e to the power of j alpha equals h of j omega, complex number. Therefore, this can very well be written as h j omega, not the magnitude, but the entire quantity times e to the power of j theta. So, what do we have now? The significance is that if you have a phasor here as the input, the output phasor is obtained by multiplying e to the power of j theta by h of j omega. This is the principle that we use in AC circuit analysis. What is h of j omega in AC circuit analysis? It is the ratio of the phasors of the response quantity, maybe a current or a voltage, to the excitation quantity, which can also be a current or a voltage. So, in general, h of j omega could be an impedance, it can be an admittance, it could be a pure ratio. We are accustomed to doing this circuit analysis using phasor concepts, but the relation of this phasor with the system function here is quite illuminating. What we are really doing is, when we have a sinusoidal function of time a cos omega t plus theta, we would somehow like to relate it to a characteristic signal of the linear system. This is not a characteristic system of the characteristic signal of the linear system. So, we view this a cos omega t plus theta as a real part of a function like this, a e to the power of j theta e to the power of j omega t. So, this is the characteristic signal whose real part is the signal which we are using. Now, so instead of using this actual signal a cos omega t plus theta, suppose we assume the characteristic signal was present, this would have been the response. But since the real part of this signal is what we are actually using, the output will be the real part of that, and that is what is happening here. Even though I have put these two steps here, actually what you can see is this is the real part of this. And the fact that the real and imaginary parts of the input produce independently the real and imaginary parts of the output without any intermixing is a property that comes by virtue of the real parameters in the system, apart from its linearity. So, instead of this signal, we are using this, and our phasor is related to this simply by dropping out e to the power of j omega t, because in AC circuit analysis what we normally have is all sources of the same frequency, single frequency excitations, wherever number of generators there may be, but all of them will have the same frequency, and therefore this omega is constant right through. So, e to the power of j omega t is a term which is invariably present both in the output and the input. Therefore, it is a term which we can drop, it is understood. Therefore, instead of writing every time a e to the power of j theta j omega t, we may as well drop both these terms from the input side and the output side and say this is the phasor for the input and this is the phasor for the output. That is what we have. So, this is how the phasor concept, the impedance concept, etc. are related to the system function HFS. In this discussion, we have taken the magnitude of the phasor to be the peak value of the sinusoid instead of the RMS value for the sake of convenience, but the same arguments will be valid even if you take the RMS value to be the magnitude of the phasor. Suppose I have a simple circuit like this, and a sinusoidal input, and this is the output, whose phasor is this, RC. Now, if this is taken as the output of the system, suppose identify this with this system and take this as the output and take this as the input, and you would like to find out the system function h of j omega in this. After all, h of s is a system function, h of j omega is also a system function when s equals j omega. So, all we have to do is take the ratio of the phasors V0 to Vi using our familiar circuit analysis procedures. This will be by potential divider action 1 over j omega c divided by r plus 1 over j omega c, which of course is 1 by 1 plus j omega c r. This is our h of j omega in this case. Once you identify this as the output and this as the input, that will be h of, that is our system function. So, analysis of systems with of the type that is described here under sinusoidal excitation becomes almost a kind of mechanical procedure, algebraic procedure, instead of our having to deal with differential equations. The fact that a system with arbitrary complexity involving a differential equation of high order can be analyzed in a purely algebraic fashion as here constitutes the central advantage of the Phasor concept and the simplicity of AC circuit analysis methods. Now, we understand here, of course, then when we talk about the output in all this, in the entire discussion here, that we are talking about the particular integral solution here. Suppose you have an input, when we talk about HFS system function and so on and so forth, normally the output is the particular integral solution. In the case of AC signals, sinusoidal signals, the common systems, the complementary solution gives rise to a decaying transients, and therefore the particular integral solution is what remains forever. It is the steady state solution. The complementary solution is a transient process. The result therefore is that whatever we are having here is not only the particular integral solution, is also the steady state solution. And if you have a system with sinusoidal inputs and you would like to observe the output and the output is sustained, it is periodic, it remains forever, then it is easy for experimentation purposes, particularly with circuits. You can find out the parameters of the input quantity and the output quantity using your instruments, maybe an oscilloscope, maybe a voltmeter, whatever you are having, measure the output phase and output magnitude in relation to the input, and calculate the system, measure the system function h of j omega for different values of omega. This is very convenient for experimentation purposes. Not only sinusoidal functions can be easily generated in the lab, but also the input-output relations can be quite conveniently measured. This is not possible with exponential signals, particularly when S is complex. Of course, it is impossible because no physical signal will have that. But even if S is real and F is real, then you may have a decaying exponential signal, which you have to do some kind of photographing or recording process. You will not be able to take measurements under steady state conditions. So, this is difficult. The upshot of all this is that characterization of a signal in terms of a system in terms of h of j omega turns out to be very convenient and fruitful one. The input-output relations of a system, if you express in terms of h of j omega, which is called the frequency response of the function system, h of j omega is called the frequency response function. So, the is a very convenient one, and we would like to make use of this facility to the extent that is possible. And what is meant by frequency response function? It is the ratio of the output phasor to the input phasor under steady state sinusoidal conditions. However, in practice, in real systems, we may not always have excitation functions which are sinusoidal. They may be periodic and non-sinusoidal. They may not also be, they may not be periodic as well. They may be aperiodic. However, we would like to make use of the simplicity of sinusoidal circuit analysis to see such situations as well. And in this task, it is the Fourier methods which come as a blessing. Is a very convenient tool for analyzing systems with these types of excitations, essentially using sinusoidal circuit methods, sinusoidal steady state methods. And it is this particular aspect that we will now take up to the form of the Fourier series. So, let me now introduce the concept of Fourier series with this background. Let us now take a look at the form of the Fourier series for a periodic function in terms of sinusoidal functions of time. You recall that a periodic function is one which has this characteristic f of t equals f of t plus t naught for all t, for all small t. In other words, if I have a basic variation over one period, the same variation continues indefinitely. And so on and so forth in both directions. In defining this value of capital T naught, which is the period, we take the value of T naught such that it is the smallest value which satisfies this equation. For example, it is possible for us to take this as the basic period, because whatever sequence of values it takes from 0 to 2 T naught will also repeat. But however, the particular value which the smallest such value is taken as T naught. So, this is the period. We also know that f naught, which is 1 over T naught, is called the frequency of the signal. And in line with what we do in the sinusoidal steady state analysis methods, we use omega naught 2 pi f naught 2 pi over T naught as the angular frequency. These are terms which you are already familiar with. We make use of them here as well. According to Fourier, any periodic function of this type can be expressed as the sum of a DC component with plus and various sinusoidal functions. It goes like this. Ft in general can be expressed as a naught plus a1 cos omega naught t, a2 cos 2 omega naught t, like that. A general term will be an cos n omega naught t, and so on up to an infinite number of terms, plus sine terms sin omega naught t, b2 sin 2 omega naught t, a general term bn sin n omega naught t, etc. More compactly, this can be written as a naught an cos n omega naught t, n from ranging from 1 to infinity, plus bn sin n omega naught t, n ranging from 1 to infinity. So, we have a whole infinite set of terms, whole lot of them. It is also sometimes convenient to combine a cos term and a sine term together, put them together, because after all a cosine, cos theta and sin theta terms can be combined, and therefore we can put them together and have an alternative notation, alternative way of expressing this. Where when you combine a n cos n omega naught t and b n sin n omega naught t, combine them together, the amplitude of the resultant will of course be square root of a n squared plus b n squared, and that we call 2Cn. Why this 2 comes, I'll explain in a moment. The angle phi n is the arc tangent of minus bn over a. we would like to use C0 and 2Cn, because later on we will see another way of expressing Fourier series in terms of exponential functions. At that time, we will use the coefficients of the exponential functions as C's, and C's that we get there, we would like to relate to these two C's. And if you express this as 2Cn instead of Cn, it will be found convenient in that context of expressing this in terms of exponential functions. So you will see why we use 2Cn when we come to that. Now let us see what it means. F of t contains, what the import of the Fourier series is, that a periodic function f of t can be expressed as a sum of a constant quantity plus sinusoidal terms of various frequencies. What are the frequencies present? Omega naught, 2 omega naught, 3 omega naught, 4 omega naught, and so on. They are all integral multiples of the basic frequency omega naught. So they are called harmonic frequencies. A naught, which is also equal to C naught, is called the DC component because it's a steady value. DC component of the signal. A1 cos omega naught t plus B1 sin omega naught t, which of course is 2C1 cos omega naught t plus P1, is called the fundamental component. And a general term, an cos n omega naught t plus bn sin n omega naught t, which will be 2Cn cos n omega naught t plus Pn, is called the nth harmonic component. So you have fundamental, second harmonic, third harmonic, fourth harmonic, and so on, an infinite number of harmonic components. And since we are calling this nth harmonic component, we may as well also call this first harmonic component, but that's normally we refer to it as the fundamental component. The fact that any arbitrary periodic function of time like this can be expressed as sum of sinusoidal components like this is an aspect which, when Fourier introduced his series, gave rise to some kind of controversy. As a historical note, Fourier is a French mathematician cum administrator. The French probably pronounce his name as Fourier, but in common with the usage in English speaking countries, we refer to him as Fourier. So Fourier, when he introduced this notation, many eminent mathematicians of his day apparently were not convinced of the validity of this. Their argument is this: Fourier said this could be extended to functions like this as well. So when you have functions of time which are discontinuous, exhibit jumps, how can you express this in terms of functions which are all continuous and smooth? All sine functions have infinite derivatives, first derivative, second derivative on ad infinitum. So how can the sum of smooth functions like this which are continuous and which have continuous derivatives, how can they add up to a function which exhibits discontinuities? So this is the problem which had to be resolved, and because of this, when Fourier submitted a paper based upon his work, apparently it could not be accepted in a scientific journal because one very eminent mathematician who was a referee seriously objected to it. In the event, Fourier finally published his work in the form of a book, and as they say, the rest is history, because the Fourier methods today find a central role in many aspects of analysis in science and engineering, and the record of the Fourier methods is one of diverse and growing applications in various branches of science and engineering. Now, at this stage, we have to perhaps a few doubts come up in our minds. One is, what type do all periodic functions have Fourier series? Does every periodic function expressible, or can it be resolved in terms of a DC and harmonically related sinusoidal functions? Second question is, if we have an infinite terms to grapple with, will it be of any great use to us? Thirdly, how do we find these A and B or C coefficients? As far as the first question is concerned, the necessary and sufficient conditions for the existence of Fourier series is a problem which mathematicians are still wrestling with. Certain sufficiency conditions are known, necessary conditions are known, but a complete set is not known. But as far as we are concerned, all types of functions that we are likely to encounter, all periodic functions, we can safely say that they admit a Fourier series description. So we need not be bothered about this and can proceed with a clean conscience in our further work. As far as the question of there being an infinite number of terms, we can say that, essentially the idea of Fourier series is that if the input function excitation can be expressed as number of sinusoids, we can find the response to each one of the sinusoids and superpose all the responses to get the total response. That is the basic idea of the Fourier series as far as circuit analysis is concerned or system analysis is concerned. A given composite function, periodic function, can be resolved in terms of various sinusoids, and we know if there is a sinusoidal driving force, we can find out easily the steady state response, and therefore we have a large number of terms. For each sinusoid, we find the response and add all these responses to get the total response. So it is in this context, that the question that arises, if we have an infinite number of terms, how are we going to grapple with this? The answer to this is that in general we can develop a expression, a formula for the nth harmonic response, and we have a series which in many cases can be combined and we can obtain a closed form expression. But even otherwise, it turns out that for most of the common functions that we are likely to deal with, the magnitude, the amplitude of the nth harmonic term goes down, decays as n increases, progressively it decreases. That means beyond a certain n, then the Fourier, the various harmonic components will be almost negligible. So it is permissible for us to truncate the series at a certain point, depending upon the accuracy which we would like to have, maybe n equals 5, 6, maybe 29, whatever it is, and then stop at that stage and take only those terms, and then if you have to calculate the value of the response numerically for a particular value of time, you can take the truncated series and then add them up. The third aspect of how we calculate the A and B coefficients, which we will take up next, but before that, let me illustrate this, how a given periodic function is resolved into various harmonic components, and how as we go on adding up the various harmonic components, the series, the truncated series comes closer and closer to the given f of t. I will refer to this figure here. Now this is a periodic function which is a square wave, which is depicted here for one period. Now if you take, in this particular case, the DC term is absent because the average of this function is 0. This is the fundamental component n equals 1, that is a pure sine wave, of course. If you take the third harmonic also into account and add the fundamental and the third harmonic, this it becomes this. This is certainly, you can see, closer to this. The next harmonic that is present in this particular waveform is the fifth harmonic. So, if you add the fifth harmonic, this is the wave that results, which is very close to this. Now, if you want to go further, you go to this next chart. If you go up to the 49th harmonic, you observe that it is almost close to the square wave. So, it is very small error exists, difference exists between the square wave and the series truncated at n equals 49. So, you can see as you go on increasing the terms, then the series, the truncated series approaches the original f of t very, very closely. I would like to show another figure which shows how different harmonic components add up to build a composite wave. Suppose this is a composite waveform that we would like to have. In this case, there is a DC term, there is a fundamental, there is a third harmonic, and there is a fifth harmonic. The composite wave that I have drawn here is one which is built from this. Therefore, it really means that there is only 4 terms in its Fourier series expansion, and the 4 terms in the Fourier series expansion are the DC term, the fundamental, the third harmonic, and the fifth harmonic. If you add up all these curves, 1, 2, 3, 4, it will add up to this. Now, let us get back to the main discussion and see how we can calculate the various Fourier coefficients.